Left off discussing how rock DNA prevents slip by mechanically allowing the concrete to pass through it. And the intersections here are actually intertwined and locked so that the fibers are braided through each other to prevent any kind of shear or peel. In conventional rock rebar or conventional composites, in any case, pull-out is an issue because the materials are inherently so much stronger than steel. Steel's been worked out to be 40, 60,000 psi, and they've got their hash marks on it to prevent pull-out and achieve an ultimate bond strength. We designed rock rebar with a Dacron, or actually we use fiberglass so that we can see it real easy, to squeeze down on the basalt fibers and epoxy as it's made to cause shape changes. The winding doesn't really have anything to do with the strength of the bar, but what it does do is force these shape changes and allow concrete to get in here and get a grip on it. And we have it worked out with the spacing and the depth of these to where we get a really good bond strength. If you're going to overlap two pieces of rock rebar, you want to do it about 20 diameters of the bar, and you're going to achieve in concrete sufficient pull-out to lap from one to the other. On the screen here is a beam test that goes a little ways to showing you the potential that rock rebar has to stiffen something in its tenacity. This beam has three pieces of 8 millimeter. 8 millimeter is a little smaller than number 3. Number 3 is like 375 thousandths of an inch. This is 352 thousandths of an inch. And three pieces of this are buried in this thing, 1 inch from the bottom, middle, and an inch from each edge. He's applying a tremendous amount of load to this, and you can see how much deflection there is in this beam. And the kid that's doing it's grinning because he's so impressed how much bend there is in this piece of concrete. When we take the load off of this concrete's going to return to straight. But it continues to apply load to it. Now it's bent and it has failed, but look what happened. It did not break or separate, part, or rupture the continuous basalt fiber or rock rebar in the bottom of it. It crushed the concrete in compression. The bending force on it overloaded, exploded the concrete on top. I believe there's a shot right after this one where the baseline test for the rock rebar was performed that went in this beam, so we knew what we had to work with. This is this piece of 8 millimeter. That's 18 inches in between here, and there are 18 inches of material buried in these pipes in an epoxy compound. Rock rebar is so strong that to grab hold of it with collets the way that conventional steel rebar is done, it easily exceeds what the collets can do as far as grabbing the material. So we have to epoxy it into the pipe of a much larger size to get a pull on it. This little green device right here is testing for Young's modulus, and in the picture right after this you're going to see what it looks like when it ruptures. It's failed. It's been pulled on now. That was around 160,000 psi of pressure was put on that material, and the failure was not straight across as you would expect, or not straight across the way that you would see steel fail. It actually sheared the fibers, but it sheared the resin holding the fibers together. Technically, this is more a test of the epoxy holding the fibers together than it is the fibers. But the point is that in a failure, the failure is very spread out in rock rebar.